In this video, we're going to introduce the topic of differential equations. So a lot of times in a scenario, you can measure the change in a quantity easier than the quantity itself. For instance, you may be able to observe there's twice as many deer as the year before, so we can measure that there's a change of 2. It's easier than like counting each individual deer. Also in cases of like movement, you can count the people going in and out of a store easier than counting like the people in the store every single time. So sometimes it's easier to think about a quantity changing rather than the actual quantity itself. And for the example with the deer, I had twice as many deer as the year before. This is saying the change in the deer over each year is twice the number of deer that we started with. All right, so a differential equation is any equation that involves the derivative of a function. Remember, derivatives are just rates of change, so just like the example we were just talking about. So any of these equations that has a derivative, here we have y prime, which is our normal derivative notation. This one also has a y prime. The other type of notation we use is like ds dt. This is the change in s over the change in t, also a rate of change. And then you can have higher order differential equations. We're not really going to talk about those too much in this class, but in college, if you're a STEM major, you might take a class called differential equation. You might do something like this, where you have a third order differential equation because you have the third derivative in your equation. All right, we'll mostly talk about first order differential equations, which is the first derivative in the equation. All right, so the first thing we need to do with differential equations for the AP exam and just in general for scenarios is to be able to create a differential equation that matches a scenario or statement. I always keep in mind this notation. The little d represents change. All right, so this represents change. And then the variables, so this would be the change in A per the change in B. So a lot of times this one on the bottom would be like a t because it's by time, right? Time causes the most things to change in scenarios, but sometimes other things change. I put kind of the thing that's causing a change on the bottom, the thing that's changing is on the top. All right, so these are the type of word problems that come up a lot. All right, so in this case we have capital P represents the pressure applied to a gas. All right, it's increased while the gas is held at a constant temperature, then the volume of the gas will decrease. All right, and then we're looking for this, the rate of change of the volume. So that's when we're talking about our differential equation. It's a rate of change of the volume with respect to the pressure. So the rate of change of the volume with respect to the pressure. So that's going to be the change in the volume over the change in the pressure is proportional to the reciprocal of the square of the pressure. So proportional means this kind of relationship, but that might not be exactly 1-to-1. Maybe there's like an extra number, like a 2. So when we're making these equations, what we're going to do is put a little k. K represents some constant. It's the proportionality constant. But in some instances that might be 2, some instances might be 1/2. All right, this case, just, we don't know exactly what the relationship is, but we know there's some constant that relates these two. It's just proportional to the reciprocal. So reciprocal means we're going to have a fraction of the square of pressure. So pressure squared. All right, so this is going to be our differential equation. It's the rate of change of the volume with respect to pressure. So volume's on the top, pressure's on the bottom. So this is our rate of change. Proportional, so we have this constant k, to the reciprocal. All right, so we're going to take a fraction of the square of pressure. So we pressure squared. All right, so that's our differential equation, and you could do stuff from there. All right, a jogger runs along a straight track. Jogger's position is given by P, where T is measured in minutes, blah, blah, blah. During the first minute of the run, the jogger's acceleration is proportional to the square root of the time since the start of the run. All right, so acceleration, how is that related to the thing we're given? Position. We learned early on that we have position. Take its derivative, we get velocity. Take its derivative, we get acceleration. So acceleration is actually P double prime of T. All right, so this is our second derivative. And that is equal, it's proportional. Again, which means we have this kind of constant k. We're not sure what the k value is, but there's some constant that relates these two things to the square root of the time since the start, and time is t. All right, so this is our differential equation. The second derivative is k times the square root of t. All right, the population source is given. Again, you can read. P of t is the number of insects. All right, t is measured in days. Right, the population increases with respect to time at a rate that is directly proportional to the population. So the population increases with respect to time. So population with respect to time increases at a rate that is directly proportional, so K, to the population. And then there's some extra information here. So starting on August 15th, the conditions were favorable and the population began increasing. On August 28th, 5 days later, there were an estimated 10 million insects and the population was increasing up to 2 million. All right, so now we're basically just going to have to figure out some of these values. So on August 20th, 5 days later, there were an estimated 10 million insects, that's P. All right, so, and the population is increasing at a rate of 2 million insects per day. So this rate, 2 million insects per day, is the rate of change of the population. We don't know K, but we know the population at that time is 10 million insects. So divide this over and simplify. K is actually 1/5 in this situation. So our final differential equation is 1/5 P. All right, so everything before here kind of gives me the general differential equation. Everything after here is a lot of extra information we don't need. We don't need like the actual dates. We actually don't need the 5 days. All we need to know is the population, because that's P, and the rate of change, that's the dP dt. So there's a lot of extra information in this problem. We're kind of sifting through it to get what we need, so we actually figure out K. All right, so here's one for you to try on your own. I pause the video, take a second, figure out this differential equation, and I'll show you the answer in 3, 2, 1. All right, so change in S with respect to T, so that should be your change. Inversely proportional. Inversely, this might be a little confusing, but you think inverse is the opposite, so that's also a fraction. So we're going to have K over the natural log of T. All right, so important things. All right, the change in A over the change in B is dA dB. So whenever they're talking about that in a scenario, you know kind of what the notation is. All right, inversely proportional or proportional to the reciprocal all means you're going to have a denominator, you're going to have this fraction. All right, and just double check to make sure your equation fits the scenario. You always want to make sure for word problems it actually makes sense.